Okay, hi everyone. First I have to apologize, I'm a bit unwell, as you can probably tell from my voice. So, yeah, bear with me. I might be a bit slow today, but nothing can stop me from working with all of you in the lectures. So, yep, apologies. Hopefully I can mute my mic quick enough before I sneeze or anything like that. I'm really excited today. We're sort of doing a new topic that's not been in 1511 before. or at least not in recent years. So I'm pretty excited about it. You can see the slides look a bit different because I whipped them up on some plane flights over the weekend, so I couldn't use Canva. So everything's a bit different today. I'm not well, the slides are different, new topic, but I think it's a really cool topic. I think it's a really interesting topic and useful topic, so hopefully you all do too. So yeah, bear with me. You're very astute with the coffee guesses. Okay, so we're talking about an extension maybe to arrays, but sort of not really. A concept that we're calling dynamic memory management, or just dynamic arrays. Incredibly useful. Hopefully today we will actually challenge a few models that you've been coming up with in COMP1511. So what you think you understand. Oh, the music needs to stop. Is that what you're saying? Yeah, sorry about that. That usually should just stop automatically. Okay. So what I'm actually hoping today is that some of the things you thought you understand about C might actually be slightly different, but that's what we want to happen. That's what I want to happen, right? So hopefully if you're paying attention and I deliver the content well, you'll make some shifts in what you understand and things will actually click a bit better. So that'll be really good. People like the music. It's good to not keep it too confusing for people that maybe attend it later. But maybe I'll do a poll or something like that and see if you like it just a bit more quiet. Okay, so that's the first thing I want to say. The second thing I wanted to say actually, which is really important. So I was at a meeting a few days ago, late last week, with the school, so the heads of department and all of that stuff. And they were telling us a story about a external student event where there were students and people from industry, maybe not even people from industry, just like people from the public at this event with UNSW students. And there was an incident where someone was making inappropriate comments to one of the students, and people that witnessed it, so other students, didn't actually sort of get up and say anything or support the student or tell one of the other staff members. So I just wanted to take this as an opportunity to say that if you're on campus especially, but even if you're online and you see something that doesn't sit right with you or doesn't sound right, you should try and do something about it if you feel safe and comfortable to do so, right? So we all have a responsibility in not just COMP1511, but as UNSW students and members of the public, that if we see something, we do say something. And you could just go call security or do something like that if you're not sure what to do. But I just want to take a few minutes to make that comment. So make sure you all support each other. University can be challenging at times, so make sure you're all got each other's back. Okay. Right on. Awesome. Okay, I'm really excited for this lecture. I'm going to just put this up a little bit. It looks a bit dark. Okay. So far, let's think about when we've been writing our programs and using variables. We request memory to store variables, right? How do we do that? We make a variable. So we can say int age or double height, something like that. We ask for some memory and we can put values in that memory. We can change the value in that memory, so on and so forth, right? That should all be something we're pretty comfortable with. And this memory, it's somewhere in the computer, right? It's in the RAM specifically, or the random access memory. So let's actually take a look at how this memory is structured or organized. Because the RAM is actually not one big blob of memory. There's actually a few components to it. If this is all new to you, that's completely fine. We've not discussed it so far in the course. So roughly, here's a representation of the memory when we're writing a program. So we have this thing called the heap, this thing called the stack. You've probably heard of the stack a few times, maybe. We have something called the code area, and we have some other memory that we're not really going to talk about because we don't use some of the stuff that gets put there in this course. But if you're curious, you could always ask. So we have these three major components. Yeah, so when you hear about Stack Overflow, that's what this is coming from. It's coming from the stack. So you're going to learn today really what the origins of the Stack Overflow website actually is, which is pretty cool. Okay, let's dive into this. So we have the code area. What's the code area? Pretty simply, When you write a C program, when you run that program, the instructions, the actual lines of code that you write get saved in the code area. That's where they're stored. So if you're running a program, it actually copies the instructions into the code area. So this is why, actually, if you've ever run a program, even like a C program that you write in the course, and then you delete the file on your computer, you delete the program will still run. Has anyone ever thought of that before? Has anyone ever thought that that's a bit weird? It's because those instructions get copied into the code area. So if you delete the file, it doesn't matter. However, when the program ends, those instructions are now gone. You can't run the program again unless you restore the file. So the code area is pretty simple. We're not going to talk about it again. It's just the spot where the instructions of your program will live. Okay. Then we have the stack. The stack is incredibly important. It stores the stack frames from the functions and procedures in your program. Okay, what does that actually mean? So if we look here, oh, and we have the heap. Sorry, then I'll talk about the stack in a moment. So the heap is where we can store dynamically allocated memory, and we'll talk more about that after we talk about the stack. So here we're going to describe the stack a little bit. There's probably going to be nowhere good, for me to put my camera, but we'll try. So let's say we've got some C code here, right? We've got main, it calls a procedure. My procedure has an integer and calls a function, and my function just sits up here at the top. So what's going on in the stack? Well, when the program starts, we always start at main, right? Main then calls my procedure. Well, we should be happy with this so far. When we call my procedure, we actually make a new stack frame on the stack that contains all the variables for that procedure. So when we make an integer in this procedure, that integer lives in the stack frame. So there's a designated piece of memory in the stack for this particular procedure frame, and this integer gets created in that frame. So then we call another function. So we make a new stack frame, and any variables or memory, for example, this integer here that goes in the parameter, exists within the stack frame. Okay? When that function ends and we go back, we actually just delete that entire stack frame. So what's important here is that any memory that we make on a frame gets destroyed when that frame ends, or when we go back to the caller. So the stack is super important. It's actually how the program keeps track of what called what and what to go back to. So if you call my function here, we go up to this my function, and this ends, how does the program know where to return? It's because it just goes to the most previous stack frame. When this function ends, or this procedure in this case, we delete that stack frame, so this integer is now destroyed, completely destroyed. And we're back at main, and then that would end, and we would destroy that stack frame too, and now we have no memory in our program. So that's actually how the stack is keeping track of the variables in our functions and procedures, and the order in which functions and procedures were called, so it knows how to go back. So how is that going for everyone? Is that making some sort of sense? So Bonrick is saying, so local variables are on the stack, and that's exactly correct. So whenever we make a local variable, for example, in a procedure, that integer only lives in that stack frame. And if we call that procedure a second time, it has a second stack frame. I've never played Magic the Gathering, but stacks are a pretty common concept, so it's whatever's on top is what goes off first. Yeah, exactly. It's like a paper pile. That's right. But the key here to understand is that this integer only ever lives within my procedure. So even if I had another integer called my value in my function, that would be a different integer, a different piece of memory, because it's in a different stack frame. And Jacob, so we can't use variables between stack frames. That's exactly the problem, well, not the problem, that's exactly the limitation that dynamic memory serves to solve. So Prison Mike says, why is it important to know where the code is stored and how much information or bytes is used? That's because when we actually do dynamic memory allocation, we need to know the size of things. At the moment, the program or the compiler knows how big an integer is. And so it's handling it for us. So in a way, you could argue that I don't really need to know at the moment, but when we want to do stuff manually, we need to know, right? Also, we're computer scientists in the making. We want to know how these things are working so that we can understand them. Okay, so that's the stack. So we can do a quick little demo here of the stack. So let's see. Let's take this down here. Whoops, what's going on here? What's going on? Oh, I'm moving the wrong window. Sorry about that. Here we go. We can close this. Oh, what's going on? Okay. Oops, can't really see all of that. Alrighty. Okay, the other thing I need to do really quickly. Oops. Save this, okay, and then I just want to make that available. All right, so let's make a procedure. So void my procedure, and let's say accepts an integer called x. Okay. When we call my procedure, we can give it a number. Now I want that number to be 5. I can pass it x here, for example, semicolon. Now, in this procedure, what I'm going to do, I'm going to take that x value here. I'm going to double it, set it to 10. And then what I'm going to do is printf, oops, this x. Now, if we look at this program, what value do we expect will be printed out here? Why don't we do a poll? Wow, yeah, it really is 50-50. Okay, let's end the poll. So 52% say 5, 47% say 10. Okay, very interesting. If we think about, well, what do we want to do? Just want to run it first and see what happens. So DCC, this is called stack.c dash output to the program file. And we get 5 printed out. let me just put a backslash in here. We get this 5. So what's going on here? Why when we passed in this variable to my procedure and we changed the value of that variable, did the 5 still print out here? What's going on here? And the reason for it is because, let's go here. When we called that procedure, for example, we made a new stack frame, and any data that we pass in as a parameter or create in that stack frame only exists in that stack frame. So when that stack frame ends, that stack frame is destroyed. So basically all this is to say is that this is a copy of X from main, not the same variable. So how many integers were declared in this program? Yeah, that's right. Witter. Yeah, there were 2 integers. That's exactly right. When we called this X, when we called my procedure and passed in this X parameter, it actually duplicated the value. So there's 2 variables. Does anyone know what this type of parameter is called? Pass by something. Temporary, yeah, good argument, yeah. So it's called pass by value. So we're basically copying the value and passing it in. Okay. Pass by value, yeah, awesome. All right. Cool, okay. So we might have a problem here. Some of you have already sort of identified that. This might be a couple problems. One, what if I wanted, if I wanted to change this here, I wanted it to propagate over, down here. I didn't want to copy the variable. I wanted it to exist and persist, for example, so that I pass it the reference to the variable, not the value itself. And there's actually a second problem, which I doubt anyone will have picked up. But when we spoke about arrays, we spoke about these variable length arrays where you can say that I want 1,000 or 10,000 items in my array, for example, right? So I can use a variable to declare how big my array is. But if we look down over here, excuse me, when we create a stack frame, the program needs to understand how big to make that stack frame. So it knows an integer is 32 bits, but if it's passing in an integer and then declaring an array that big, the array might be bigger than the amount of memory that is allocated for the stack frame. So this is actually the reason that if you go to the course website, which I probably should have had up, here we go. If we go to the section on variable length array, we say don't use these types of arrays where we pass in a variable as the size of the array, because the program might not know how much memory, it might not have enough memory on the stack frame to handle it. But that's a sort of a thing to know. So basically, it might not have enough memory to handle it. So all of this is to motivate that we need a way to manage memory ourselves outside of the stack frames. Because A, the stack frames might not be big enough to do what we want to do, and B, we might want our memory to exist and persist outside of those stack frames. Does that make sense? So we don't always want our memory to be just, yes, Thanos snapped when the stack frame ends. Anubis says, well, why don't we just make the array really big so that there's no conflicts? The issue is that if I just pass in an integer to a function to declare the size of the variable length array, it won't know it won't know that how big that array needs to be on the stack frame. So it's not going to, might not work. Okay. And this is exactly what the heap allows us to do. So the heap is another block of memory that exists outside of the stack and of the code space. And it's a space where we are able to just request data, maybe a bit here, for example. And they persist, as the stack frames are going, right? So they live on this data in the heap. But that has some implications, which means we need to manage when we create that heap data and when we destroy it. We need to handle that all ourselves. This is where we come up with these memory leaks in our programs, when we declare some heap data and then we never actually free it. Fake Olive says, are concerns about memory only valid in low-level languages like C, or do we have to consider this in Python and Java as well? It's a great question, and you're sort of right. Generally, the higher the abstraction of language we go, for example, Python, we don't handle data like this very often, if at all. We don't use pointers pretty much. Well, pointers are used everywhere in Python and Java, but the language handles it for you. Whereas in C, you have to handle them yourself. But they are used everywhere. Oops. Okay. Amazing. Well, sorry, I know that's not how you say it. So the heap is like global data. Yeah, it's like data that we can access at any time, as long as we have a reference to the data. Joe says, well, what's the advantage of handling it ourselves? Great question. Some people will say there's no advantage and that we should let higher order languages like Python and Java, for example, to handle it for us, because it's less likely that we'll make mistakes. But if we really want to get our hands dirty and really optimize our programs, you need to sort of get into it, right? You need to first of all, you need to understand that this is how even higher level languages work. And second of all, there are cases where, so even sometimes where people will write like a C++ program or something like that, and if they really want to optimize some critical function, they will actually modify the assembly code itself to increase the speed. So I know game engineers do this a lot because performance is really, really important in games programming. So that's an example where when performance really, really, really matters and someone really, really knows what they're doing, you may actually want to jump into the memory and handle the pointers yourself. But generally, if we want to be proficient programmers, we're okay to use higher level languages like Python and Java that basically handle this all for us. But it's important to understand it. Okay. So if we have this heap, how do we actually access it? How do we handle it? What's going on? And to do this, we use pointers. So pointers are a variable like all other variables, like your integers, your floats, or your characters. But instead of storing a value like, 30 or 40.5, it stores actually a location to memory, somewhere in the RAM. So if you look back at this grid, a pointer will just, store one of these grid elements, the location of it. Oops. So they are a variable which store a memory address. There's two new operators that we need to understand when we're looking at pointers. So we have the address of operator, which is used to look at a variable and find the address of the value. And we have the dereference operator, which looks at a pointer. Oh, there's an issue with there's an issue with this slide. So the address of operator looks up the address of a value. So if age is an integer, this will actually return the memory address of the variable. And the dereference operator does the opposite. So if we have a pointer, it will find the actual value in the pointer. And we'll do a demo on this. But to go over that one more time. So when we make an integer called age, and we say that that value is 25, it goes off and creates some memory, puts the number 25 in it, but that memory has an address, right? And that address is actually where the value 25 is contained. So then if I was to say, well, make me get the address of that value and assign it to another pointer, what we actually have now is a pointer that stores the reference of where that other value was. And when we look that up, we get back that original 25, or in this case, the memory address. So Tracy says, I'm a bit confused. Why do we need the addresses? Great question. A few reasons. One, it's how we can store our references to the heap. And two, it's when we want to pass something to a function or a procedure and modify the value and have that modification. You're not duplicating the parameter. We'll do a demo on it and maybe that'll help make a bit more sense. Okay, so let's do some pointer demos. Let me close this. Something's a bit wrong there, but anyway. I know. Okay, gedit. Let's go pointers.c. Whoops, I didn't. Oh, that's fine. Okay. So let's do now you can follow along. Oh yeah, I do. You can follow along here if you want to write this code yourself. It might be helpful. Okay, lots of chat questions coming in. Let me give it a sec to read them. So Noah says, when we create an integer, it's always stored on the heap. No, when we create an integer, for example, here, it's always stored on the stack, unless we create a pointer. Well, unless we use something. We haven't actually looked at how we get heap access yet. The error in the terminal is nothing we can fix. You just ignore it. Because it's an old version of gedit or something like that. Okay. So first of all, with pointers, I wanted to show you one of the things we do with pointers. On the stack to modify values. Actually, let me say to pass by reference. Okay. Yeah, that's right, Jacob. You've not been using any heap memory whatsoever. Okay. So let's do the exact same thing. So we have an integer. We'll call it x. We'll assign it the value 5. We'll call my procedure. And we'll say, give it the value x, but not the value x. So don't copy the value. give my procedure actually the address of that value x. Okay? That's what the ampersand does. So it says, give my procedure the address of x. Now that says, okay, my procedure needs to accept an integer, but not an integer itself. It needs to accept a pointer to an integer, or the address of an integer. Okay. And now we can say x here. We should be able to say x is equal to 10. And then here we should be able to printf %d \n x. I think this is okay. Is this going to quit actually if I, yep, because I didn't put the ampersand here. Hopefully that's saved. Thank goodness. Pointers.c -output to program. Okay. Okay, so this at the moment is a pointer to x. So what we need to do is say that the I'm missing void. I'm missing void here. Now I thought I could just do this. It's not important, sorry, Bonrick and Jacob. We're just being more explicit here by saying that there's no parameters that go into the main function. Okay, can you explain the *x, Anubhav? Yep. So what we're saying here is that we don't want to pass in an int, we want an address to an int. Excuse me. Okay, so I've never actually run it. Probably that makes sense. All right, this is super interesting. So what's happening here is that we're using pointers to pass not the value in the variable, so not the 5 itself, but we're passing in the address of this variable. In the arguments, we can say, I don't want an integer, I want a pointer to an integer. That's what this is saying here. An address or a pointer to an integer. And then here we're saying, follow the pointer, right? Follow the pointer to x and get that value and change that value to 10. So if you remember back before, this still printed out 5 when we just passed the integer itself. But when we passed the pointer to the integer, it actually did change it in my procedure. And so when we print it out here, we're actually getting that 10. So what's the benefit to this approach? Yeah, the ampersand means the address of a variable. That's exactly right. The ampersand is like sending the address. The star is to get the access the memory that the variable is pointing to. So Matthew says the value of x is constant. I see what you're saying. I wouldn't probably word it like that. I would be saying that, yeah, well, there's only one integer in this program, actually. That's the value. There's only one integer, whereas before, we made a copy to the integer. So this is a very basic demo of pointers. But now, so question, is this on the stack or is this on the heap? Is this integer on the stack or the heap? So Elizabeth says, is it changing the value of the integer in the stack of main, or is it variable located on the heap? So we can do a poll. Sorry, I keep asking you questions and then I do the poll and then everyone has to answer twice, which has been doing. But maybe it's like it gives you a warm up. Yeah, we love our 50-50 polls. Okay, that looks like it's stabling, and of course, it's right at 50%, which probably means it's a good question. So, even though if you look at line 12, right, we just made a bog standard integer. Do we all agree? This is just a normal, you've been doing this all through COMP1511. Whoops. It's just a normal integer. Therefore, it's made on the stack, like all the other integers and floats and characters that you've been making. So it's still on the stack, but we're getting the address to the stack here. So this is still all on the stack. So we haven't actually done anything with the heap yet. We'll do that next. But pointers are the first building block necessary to interact and handle the heap. So this is one of the two building blocks we need. But yeah, it was 50-50, but that means it's a good question, right? So that means it's something that we do want to clear up. So yeah. So all memory is memory. So if we go back here, oh, I gotta go way back. If we go back here, all of this is just memory. It's all in the RAM. So you can get an address to the stack, you can get an address to the heap, you could even get an address to the code area, but let's not worry about that. So if we make a variable on the stack, we can still get the address of it, and if we make a variable on the heap, we have the address of it too. Now I gotta go all the way forward. Okay. Right, we've done all this. Okay, so that's pointers. Now, how do we use pointers to interact with the heap? Anubis says, can we do the example of pointers only in the main function? Yeah, we absolutely can do that. So I think what you're saying is, well, okay, how about this? Actually, not a bad question. Why don't we spend a bit more time on pointers, because we are tracking pretty good for time, and show you some cool stuff we can do with it. So if ampersand gets the address of x, that means we can print %p, the pointer, there we go, the address of x. I can just get rid of this procedure. And look, I mean, this is pretty cool. That is literally, on this machine, the address of where the integer x was created. I mean, it is pretty cool. That's correct. It's a hexadecimal value, which is referring to the address in the RAM or in the memory that this program owns. Bronrick says, does it change? Good point. We do not control where our stack variables get created. So 100%. And it could be that when we run the program again, in this case, it's staying consistent. But if I was doing other things with my computer and the memory was shifting around, it might be a different address. So this is not consistent. The %p means print the pointer. It did change? Oh, it did change. It just ends in a 60. Yeah. I mean, it makes sense, right? Like, I start the program again. It's not necessary that the operating system gives us the exact same piece of memory and stuff. Yeah. Someone asked a good question. How big is a pointer? 8 bytes. That you were 100% correct. 8 bytes. Yeah. So AR11 says, if you knew the addresses, could you inject it into your own code? This is now getting more into hacking than programming. It's unlikely you would know the addresses. So Joshua is saying, why does it change? It's because, remember when we spoke back about variables and memory, what happens when you make a variable? We ask our operating system for the data, right? Remember we keep saying that? We ask the operating system, we're like, please, can I have some memory? We don't know where that memory will be. It gets given to us, right? We politely ask, that's right. We very politely go up to our operating system and we say, can I please have some memory? And it goes, fine, here's some memory. So we don't know, we're not deciding where that memory goes. Okay, Zed Vance that's a fantastic question. So Zed Vance says, is this, I know what you're saying, does this link to why we're using the ampersand when we're calling the scanf? So remember when we call scanf, whoops, that should be a %d. We give it, remember we're always giving it %x? Do you remember we've always been doing this? Right? Well, now we know. What does this ampersand do? It gives it the address of x. So what actually happens here is we give scanf the address of x so it knows where to put the value that gets scanned in the memory. So what scanf is doing is it's going, you give me some memory address and I'll put the value in. I mean, it makes sense, right? Otherwise, if you just get the value 5, otherwise it's like, that would just be giving it 5 and it would be like, oh, what do I do with this? It's just the number 5. Now it's the address of my integer. So scanf can override that memory at that address. Bonrick says, does that mean the pre-made function of scanf has a pointer variable somewhere? 100,000%. I mean, you guys are absolutely killing it. I wonder if we can even get up the source code of scanf. Okay, so, I mean, this is sort of going to help and sort of not. It's not as simple as we would hope. But, so this is actually, here, the internal scanf function declaration. So it's a function. I'm trying to make it a bit bigger. I've just lost it now. Here we go. So scanf, this is the internal scanf. So you call scanf and it calls this. It returns an integer. And you can see here, this is actually the list of parameters, right? Because it can be more than one. And you can see they're called argument pointers, arg pointer. So yes, it is accepting a pointer to the argument. But that's not as sort of clear as we would hope. because it's accepting multiple. Okay. So Nikhil is saying the second one wouldn't work since %x is not an int. What are you talking about here? So when we do stuff like x++, we don't need to point to no, because we care about the value. We're not scanning in the address of the int x here. This is how we scan in a new value into x itself. AR11 says, why didn't it have both the star and the ampersand built in? Are you talking about the scanf? What's going on here? Oh, it was just... Oh, it was scanning, that's why. There we go. Okay. Bonrick says, oh true, why doesn't scanf just accept something without the ampersand and automatically place it there itself? What a higher language would do. Okay, that's an excellent question. How do I answer this? So the higher level languages, after the abstractions sort of get applied, they are doing exactly this. It is passing the address of the variable. In fact, if you look at a language like Python, almost everything in Python is a pointer. Everything. Every single piece of memory you make is not actually an integer or a string or anything like that. It's the pointer to that object type. So those languages are doing this, not the other way around. Does that make sense? C doesn't have those abstractions, therefore we have to do it manually. Yeah, I didn't know what you meant by the inspiration either. Daniel? So Fake Olive says, does that mean higher level languages are also less efficient with memory usage? Yes and no. In general, a lot of smart people spend a lot of time really optimizing higher level languages, but yes, there's a reason why C is always going to be a very, very fast execution environment because it has no abstractions it needs to do. C is so powerful because it lets us do absolutely everything very manually, but it also means there's a lot of ways we can break our programs. Jacob says, since pointers are 64 bits, does this relate to how many memory addresses exist in RAM? So the pointers are actually 8 bits, not 64 bits, but they run on 64-bit machines. That's when I think the shift to 8-bit memory addresses occurred. Okay. Alright, is there another demo, maybe Tammy or Noah, is there another quick demo we can do in the next 5 minutes with pointers just in this file that might show off what's going on with them? Oh, 64 bits, sorry. Yeah, you're right. Sorry about that, I misread it. Now, I'm scared to tell you guys, I don't have a Kahoot ready. So, I don't know about that today. Oh no, I'm so sorry. Maybe I can try and make one before the end of the lecture, really quickly. I've been unwell, I'm sorry. Don't hate me. I got dethroned, yeah, that's right, I had enough of losing. Yeah, there was a Kahoot yesterday, that's right. Kahoot replacement keyboard reveal. We'll see. It is week 4. And you've been asking excellent questions. Okay. Anubov says, oh, I know what we can do, actually. That's a good question, Anubov. If ampersand x is the address, how do I change the value of x just by using pointers? I tried it and it said you're using x as a pointer. That's a great question. Let me copy this in and we can actually solve this. In the meantime, someone asked why OS is called 32 bits and 64 bits. So it's literally the fact that memory... So if we had 32-bit pointers, so our memory was addressed using 32-bit pointers, that means once we hit the limit of 32 bits, we're out of memory, addressable memory. So what happened was memory started off with very small amounts, like in the kilobytes. Okay, then we got gigabytes of memory, 1 gigabyte, 2 gigabyte. At some point, right, as you're expanding all your memory, you run out of pointers that can address all of the memory. Does that make sense? Because it was only going up to 32 bits. So yeah, as Fake Olive said, 32 bits can refer to roughly 4 gigabytes of RAM as maximum. So the moment that hardware engineers were able to produce sticks of memory or pools of memory greater than 4 gigabytes, there was a problem. You couldn't address it. You couldn't make a pointer to it. You couldn't get it. You couldn't refer to it. So the operating systems had to change everything to work using 64-bit pointers. Does that make sense, Daniel? And thank you, Weena. That's very kind of you. Okay. Will there be a day when 64-bit pointers aren't enough? I think it's a lot of memory. I think it's a lot. Yeah, it's a lot. It's a real lot. 60 billion gigabytes. Sorry, that's making me laugh for some reason. So I think we might be fine for a little while. I think I'll be long dead before, if this flu doesn't take me out, before we hit this limit. Yeah. So I think we're good for a while. But I mean, this isn't the first time we've seen something like this happen. Does anyone know the other example that I want? Do you happen to know the other example where we hit an artificial limit that our systems implemented? Y2K, that's not what I'm referring to. That's a bit different. Actually, that's sort of similar. YouTube, no. No. Not integer overflows, although I see where you're all going. Gangnam style. No, it's when we ran out of IP addresses. IPv4 addresses are running out. As of 2019, the last remaining addresses of the available pool had officially run out. And it's a similar system, so IPv4 could we thought that would be more than enough addresses to store to refer to IP addresses, for the end of time, and it definitely wasn't. So IPv6 max addresses is now 3.4 times 10 to the power of 38. So roughly 340 trillion IP addresses can now be stored by the IPv6 protocol. Bonrick says, why did we think that? What a good question. What a good question. We just weren't able to predict how fast things would grow. If you look at IP addresses specifically, if you look at early networking, so like what DARPA were thinking about, back then when they were designing this infrastructure, it was thought that you would have one big computer for like a university, maybe one in a library, that, we didn't even know that we would all have a computer in our home. And now you've got a phone, a smartwatch, a computer, a laptop, an iPad, you're consuming 6, 7, 8, maybe 10, your TV, anything that's networked needs an IP address, right? So the idea that you would have this one big computer, computers are expensive, you might get some time sharing on it. 2, every person has 15, 20, 30 IP addresses. Of course, we ran out in 2019. There was still a lot that we were able to facilitate. So now we're in this painful switch to IPv6. We just underestimated our ability. Well, I don't know it's our ability to mass produce. I think it was our ability to get things really small and make it really cheap. That's what's been amazing. Okay, I've got a bit off topic. But that's okay. Let's have the mid-lecture break. I apologize again, there's no Kahoot. If I can figure out a way to show you my keyboard or something, hopefully that'll make up for it. But yeah, exactly right. We have 10 devices occupying our attentional space all the time. This is why, we struggle watching the lectures. I can't believe I've been skipping cool lectures. But I've seen your name here, Bonrick. Okay, I can show you the keyboard. I'll show you... all right, I'll show you the keyboard. Who's ready for a keyboard reveal? But I got to get my phone out of here. It's a very complicated setup. But you've all been sort of sleeping because... What's happening here? Is that working? What's going on? This is really confusing. Hold on, let me go. Can anyone ID it? It's very blurry. Is it really blurry? What is going on? Okay, how's that? So it's a GMMK Pro with Black 2. Yeah, how did you know that, Callum? How did you know that? That's scary. Okay. It's on the website. No one even realized. No one looked. Yeah, exactly right. The details have been on the website for like the whole term, and so everyone's like begging for the details in the lectures, but on the course website. Because people ask a lot. No, I'm really... Okay, where's... Oh, I look awful. Anyway. Yeah, there's a TV in the background. Okay, espresso machine, we can do another day. No. Okay. Okay. All right, let's have a mid-lecture break. I hope you're all happy that you saw the keyboard. Okay, special machine can be the next one. All right, I need to go make a tea or something like that. I'll see you all in 5 minutes, and then we're going to talk about actually how we can allocate memory on the heap, which is really cool. Okay. Okay, that's got to say that's the most confusing mid-lecture break discussion I've ever seen. I would love to find out what's happening with that website. I'll post a photo somewhere, Joe. Over when I was in Melbourne and we were in the long lockdown, I built the keyboard. So I disassembled every switch, lubed every switch, custom stabs, everything. And then I bought the Rama Works keycap set like over a year ago, and they're still, I haven't heard anything, but so these keycaps are just temporary. Yeah, I don't know. I should join the Keepsock. Someone's going to tell me how I can join. Okay. It's a cool hobby. It's an expensive hobby. All right. Okay. Let's close this. Yeah, you should all definitely join a society if you can. It's really good. Okay, so we've done a lot in this lecture. There's one more thing I want to talk about, and that's actually how, and it's the combination, right, of a few things. So it's how we can actually use pointers to access memory on the heap. Why is this video playing in the background of the tab? I'm confused. Anyway, is there something wrong with my setup or something else? Okay, I don't think it's me. So I just wanted to say briefly, if you're a bit confused with what we've spoken about today, that's okay. I would say as fundamental concepts, pointers and memory may possibly be the hardest sort of base concepts or building blocks to get our heads around. Pointers are a very abstract thing. You know, an integer being a number, that makes a lot of sense. And a pointer to an integer that stores the memory location where that value is stored. It's just one more level of sort of abstraction that can take some time for us to get our heads around. So if you're a bit confused, that's okay. But like I said, there's one more building block we need to talk about today. And that's how we can use pointers to interact with the heap. So far the pointers we've been using have been on the stack still. How can we do that? Actually, this line might look very scary, but it's not too bad. And this is all you need to get data on the heap. So basically, there's two functions here that we're introducing. So if we want to access the heap, we need a pointer to the heap. So therefore, if we want an integer on the heap, we need an integer and then a pointer to an integer explicitly. And we're just calling this a variable, an integer on the heap. So pretty simply here, I'm declaring a variable. What data type does that variable store? We'll talk about malloc in a moment. Okay, be careful, right? Be explicit. What data type is actually stored in integer on the heap? Yeah, so some of you are getting it. It's not an integer, it's a pointer to an integer. It's an address, that's correct. Because the star is here. Address of a pointer. Exactly right. Okay, so we're saying, I want a pointer to an integer, all right? It's going to be assigned. Now, we have a few things here. So the first thing is, before we call malloc, which I'll talk about in a moment, we need to compute how much memory we want on the heap. So heap memory is really, really sort of, you have to tell it everything. So if you want an integer on the heap, you need to say, I want enough memory on the heap to store the size of whatever the data type integer on heap is, which is enough memory to store an integer. Right? So first of all, we're saying, give me the size of an integer. So how many, what's that going to be? What's that going to evaluate to? Exactly, 32 bits, because that's how much an integer is required to store. So it's not the size of the pointer. This is actually doing the size of the integer, which is 32 bits. And then we pass that 32 bits to a function, a special function called malloc. Now malloc takes the size, so 32 bits, and it just very simply does a memory allocation, malloc, for 32 bits. That's it. It's that simple. And then what does it return? What do we think malloc returns? Yeah, Nicole says the pointer. Exactly right. It returns the memory address of where that memory was defined and assigns it to integer on the heap. And that's pretty simple. That's it. If we get the pointer by calling malloc, it's on the heap. Now, some of you, if you look at C code online, you might actually see that you can do size of int, the data type. This is what most C code does. However, by using the variable, it's actually more flexible, because if you change the type of the variable, you don't need to change the malloc. So this can actually be a little bit more simple. Okay. Yep, so can we see an example of this? Absolutely. All right, so let's close this and open up my, let me actually make a new file called malloc basic. Oops. Now I think actually, yep. So to use malloc, you need to import standard library. And then standard IO is what we always, import. Return 0, that's fine. Okay. Now, let's look at our slide. Well, basically, let me see, I can probably remember. If I make an integer, and I want to point it to an integer called, my age p, because it's a pointer, and I'm going to assign it the return of calling malloc, the size of my age p, semicolon there. All right, let's just see if that compiles. Clear this, DCC, malloc basic -o to program. Does that compile? Yes, it does. If I run it, it's not going to do anything, but that's fine. We take our steps. So now, this integer is memory on the heap because it's the result of calling malloc. Malloc comes from standard library, AR11. So it's just where it exists, just like scanf and printf exist in standard IO. But now I can do anything with that integer. So I can say printf yeah, so it's okay. Noah, what's the benefit of calling memory from the heap? I'll show you in a moment why we need to do it. But okay, let's see here. Oops. I think this should work like this. Cool. So we can make a pointer on the heap. we can dereference the pointer and assign the value 10, and we can print that out. Now, at the moment, like this doesn't make much sense for why I would use the heap, because you could just make an int on the stack, for example. So the size of function takes the size of either a data type that's passed in or a pointer and dereferences it. So this is going to get the value at the pointer, which is an integer, and then it just gets the size of the integer. Okay, so Elizabeth says, if you declare a variable on the heap in a function, will it be deleted with the stack when the function ends? And that is exactly why the heap is useful, because the answer to that is no. So if we made this, right, if we create an integer on the heap, we return the pointer to it, we do something like this, then we return my age p as the pointer itself is equal to create integer on the heap. I'll assign it here as well. And we print it. I think that should work. And we get that 10 printed out. Even though create integer on the heap, we exited that stack frame. The value still exists. The memory was not allocated on create integer on the heap's stack frame. It was created in the heap. So AR11 says, how does the return relate to memory? Do you mean this return here? Okay, Alvin Seed said a really good question. Sorry, let me just blow my nose really quick. So we raised a good question, right? We created this data on the heap, but we then printed out. What if we want to delete that data? Because when we use the stack, the data gets deleted as the stack frame gets removed. How do we delete data from the heap? We pretty simply just use a function called free, and we pass it in a pointer, so my age p, for example. And that's going to delete that data there. What would happen if we then tried to print it? I actually don't know. It might just print some garbage data. It might even just print 10. There you go. It actually crashes. I'm trying to access memory that's already been freed. That's pretty cool. Will the function refer to a different address each time it's called, or only the same one? It's going to refer to, it might be different, just like earlier when we made a pointer. It could be different every time. %p prints the pointer address itself, that's right. Okay, we all answered the question. Awesome, Freedom. Can you please talk through the code once more? Absolutely. Free means delete, correct. Yeah, it depends on the compiler. That's exactly right, Fake Olive. Okay, let's talk about this. I have a function called create integer on the heap, and I made a pointer to an integer. I call create function on the heap, right? So let me annotate it. Create a pointer to an int, call the function, and assign the result. The function's over here. Create some memory on the heap for an integer. Okay, so create a pointer to an integer and assign it the pointer returned by malloc creates some memory on the heap. We can then assign it a value by dereferencing it and return the pointer itself. So now we have a pointer to an integer, but the integer lives on the heap. Now, some of you are asking, blah, blah, blah. Over here, you can also do size of int. So you can do size of integer. This is what I was saying. Most of the time, when you look at C code, you will see something like this. I actually personally prefer that you pass in the pointer of the, or you pass in the value, so you dereference the pointer. Why is this better? Does anyone know? You'll see both. I'm not saying like this is awful. In fact, a lot of the tutors may do this. Exactly right. Noah's got the reason. If I was to change the size of the pointed value, it would just automatically update. I don't have to change it twice. It's just a little bit more dynamic. Exactly right. Yeah, exactly right. Exactly right. All right, a lot of questions, and that's really good. What happens if there's a mismatch of the heap allocation and the variable being read to it? So if you try and put too much in the pointer, is that what you're saying, Elvin said? Intrinsic documentation, yeah. Exactly right. What's the point of line 19? Well, I need to keep a reference to the memory that was created in the function. So I need a variable for it in main. Okay. Light Cursor says, why is this better than using a global variable? So a global variable is different because a global variable is just automatically accessible by all functions in the program. This is only accessible when it's passed into a function. So it's not a global variable, it's just a variable that I need to explicitly pass to each function. Globals don't use more memory, Bonrick. It's not that they use too much memory, it's just that they're globally accessible. Whereas this, so I can understand why you're sort of saying this and why you're getting confused. I create my pointer to the heap here, but it's not, if I have like another function here, right? Right? Oops. Does this have access to the heap integer that we made? Ooh, good question. Okay, so some people are saying yes. Some people are saying no. Yeah, the answer is no. The answer is no. No. I don't know the pointer address. I don't know how to access it. I don't know what the value is. It's not available. I can't use my age. That doesn't exist here. So it's not global. The variable is not global. Whereas if I had a global, int x or something, I would be able to just use it here. It's global. The problem with globals is that they're global. Not that they're, it's that anyone could change it at any time. Whereas with my heap pointers, I still need to pass it into the functions. Yeah, I don't have the address. That's exactly right. Yeah, that's right, Nicola. It's like walking up to a house and not being in because I don't have the key. Well, it's like I don't even know the address of the house. Alvin said, can you manually assign a heap pointer? No, because you need malloc to ask the operating system for the memory. Okay. All right. Okay, I made this tea way too strong. Can you manually sign? Okay, blah, blah, blah. Yeah, globals mean you could get lost very fast. That's exactly right. Justin, why do we dereference the value, the variable on line 13? Why can't we just make it a normal integer and initialize it with a value? Line 13. When we want data on the heap, we need to have a pointer to it. It's just how we interact with it. Because we are managing the memory, not the program. So we need a pointer to it. Jacob, why do you have install for create an integer function? Again, we want the pointer to the memory on the heap. It's how we interact with the heap. Noah, on line 24, we assign the output of create int on the heap to the pointer of the variable myHP. That's correct. 33 split. Okay, yeah, let's look at the results. Okay, 37% are confused. God, we love evenly distributed polls here. 37% I'm confused, but let's keep going. Move on, 24%. So, like I said, it's okay to be a bit confused. This is a complicated topic, but I wanted to get it in now, and I didn't want to hold back. I promise, like, if you spend the time and get your head around this stuff, you're going to do so well in this course and as programmers in general. So I really think it's important. I have one more thing I want to show today, and I think it's a really cool thing. So Matthew, if you do the star before the int, it allocates it to the heap. No, it's when we call malloc that we get allocated on the heap, but we still need a pointer to the heap address. What's the importance and advantage of manually putting data on the heap? I'm going to show you right now, I think. So when we let the computer organize memory, it'll use the stack method, whereas if we want to manually control the memory, we use the heap and pointers. That's exactly right. Exactly right. That's exactly right. What's the maximum size variable within the heap? Good question, Elephant Seed. What it does actually is it figures out how much memory the stack needs and makes it the frame as big as it needs to. So it tries to be dynamic. But yeah, so 74% are saying I'm a bit confused, but I mean, in some ways, my goal is to confuse you, right? If you're confused, that can sometimes be a good thing. And then as you do the tutorial activities in the labs, you will understand it, right? If you were never confused in this course or as a student in general, it means you're never actually learning anything. That's my sort of perspective. But it's a balance, right? So it's always hard. I can assume we can point to an array as well. Nikhil, you are you're stealing my thunder. That's what we're about to do next. Bronrick says, wait. Windows, you're right. Okay, cool. Okay. All right. So what if we want more data on the heap? What if we want an array, for example? I mean, this is it, right? What's different here? We're getting the size of the integer, so the size of an integer, 32 bits, and we're multiplying it by the size of our array. So with this small modification here, what we can actually do is declare an array on the heap, a dynamically sized array on the heap that will be accessible anywhere we need it. And you can imagine, right, it's not just arrays that we can put here. If you're really being really a control freak with your programming, you can just declare any sized piece of memory on the heap and access it and put bits and take bits out. But this example, right, is going to declare a pointer to the heap. So let's go we already have malloc here actually. Cool. Okay. So I got a little program here that I want to write. Ooh, what have I done? So int main, we can put void here. We can say return 0, that's fine. All right. What I want to do here, make a program that makes an array on the heap and can be really dynamic with it. All right. So why don't we declare the array, and actually these should all be on the one line. Sorry about that. Breaking the style guide. Okay, almost there. All right. So first of all, we need some array size. And we have this base array size. So I've got 12 elements in my array. That's fine. I need to make an array on the heap. How do I do that? Well, I can say I want a pointer to, let's just store an array of integers. So I need my array, right? It's a pointer to an array, and it's going to be assigned the result of calling malloc with the type of the value of array, so the size of an integer, multiplied by the base array size, semicolon. Excuse me. Okay. So this makes 32 bits times 12 on the heap. All happy so far with that? Okay. Then what we can do is we can call this initialize array. Let me just see, actually, did I have another slide? Whoops, okay, no I didn't. Well, I did, but I'll show it later, that's fine. So I've declared enough memory on the heap for this array, and I assign it. The question is now, like, let's say I want to put some data into that array. So let's call, well, let's just do it here, right? So we can do it, whoops, while, we can go int I equals 0, while I is less than base array size, right? So I can loop through 12 times. Now here's the thing that I want you to, oops, that should be size of. Yeah, you're right. Thank you. Here's I think the mind-blowing thing, right? This is what I've been leading up to the whole lecture. So everyone take a pause for a second. I think this is really exciting, right? When we declared an array, how do we access that array, right? Like, how do we access the elements of the array? We can say like array of index 0 is equal to 10. But I didn't make an array, like I just got some data on the heap. So how am I going to do this, right? Like, how am I going to tell C that this is an array, right? Like, do you know what I'm saying? Like, I didn't make an array. I just have some data on the heap. And here's the really cool thing I think about arrays in C is that we've actually sort of been lying to you this whole time. There is actually no such thing as arrays in C. What? What are you talking about, Jake? This flu is making you sick? There isn't. An array in C is literally just a pointer. And so that means I can literally do array bracket I bracket equals, for example, I. That's it. That's it. That works. This array, this is an array. Anytime you made an array, my array, it's literally the same as a pointer to an integer. That's it. It's the exact same thing. Everything is a pointer. Pretty much everything is a pointer in C. That's exactly right. Done. And that's it. So for example, if I run this loop here, let me get rid of this. It's going to assign all the indexes up to I in that array. Now, maybe you don't believe me. That's completely fine. Why don't we copy, whoops. Why don't we copy this, paste it, set I back to 0, and let's just printf %d array of I like that, we should see 12 okay, that's fine. I think that's just saying that you're not actually returning anything here. That we can just ignore that because we're not calling it yet. We run program. Something's not right here. Oh, I didn't, sorry. Yep, I didn't add. That's what I forgot to do. Yep, thank you. Oh, there we go. Let's just go, you know, like that. Oops. And we get our 11, or our 12 values printed out. How cool is that? However, this array is still, it's still on the heap because I got the data from calling malloc. Does that make sense? Now we can put this initialization into this function, right? To make everything quite nicely. We pass in the array, we pass in the size. So let's actually use size here that we'll pass in. And otherwise, that is exactly the same. So this is pretty cool. Like this procedure doesn't return the pointer of the array. It's just filling it in. So what we can then say is, we can then say, you know, initialize array, passing in the array, right? We pass the pointer, because we have a pointer. We pass the pointer, and remember, a pointer, or an array, is just a pointer. Same thing. Therefore, we can fill it up in this procedure without doing it here. Oops. And that means we should get the exact same output. Oops. I've got to, whatever. I've got to say int here. All right, I've got to pass in as well the size. Okay, and if I run this, we should get out 11 values printed out very nicely. Okay, Bonrick says, why does, wait, does the heap exist outside of the code? What happens if we forget to free the data? Good point. If we don't free the data, when the program ends, the data will still be freed. But if you have a long-running program, that's how you can get a memory leak. Okay. Okay. That means we can also separate this logic to print the array here. Oops. That's nice there. So we can initialize like this. We can print it like that. Let's make sure that works. That's printing out quite nicely. Okay. Now there's one more thing. Whoops. There's one more thing I want to show you. Let me delete this. So we can make an array on the heap. We can put some data into it. And we can print it. What if now, like we're talking about, we want dynamic memory. Oh yeah, that should be size. Good catch. We want dynamic memory. So that means we might fill our 12 elements and then we might say, well, Jake, I want 24 elements now. I want more data in there. How can we do that? And the answer is, and I think I've already accidentally closed it, but there is a function similar to malloc called realloc that allows us to reallocate an array with a bigger size. So how do we do that? Well, and let me, just because we have only 9 minutes left, let me copy this code in. Whoops. Never mind, that didn't work. Okay. But we'll run through it. So we accept an integer array and the current size. We make a new pointer to a new array. In fact, I could just do this on one line. Right, so this new temporary pointer. And we call realloc, right? Which is like malloc, but reallocates memory and copies in the data that was there. So it's called very similar to malloc. You call realloc, except you also give it the memory, the pointer that you want to reinitialize or to reallocate, and then you give it the size again. And so what we're doing here is we're saying we'll take the size of the array and double it. Doubles the array size to, in this case would be 24. It should be on the same line. And then we just make sure that worked. So we make sure it's not null. If it's not null, we can reassign my integer array to be that new pointer address, and then we can just return it. Else we return null because something didn't work. Maybe we tried to request too much data. Yeah, I've gone over the line size here. Okay, one line over here, but that's okay. All right. Now what that means is that I need to track the new size of the array, right? So rather than just using this base array size, because it's not going to be kept up to date, I can just say array size is equal to the base array size at the beginning. I'm going to start using this. Whoops. Blah, blah, blah. Do this here. Do this here. And so that after I initialize it, I print it, I can call this, what did I call it? Double array. Pass it array size, and then I can say array size is equal to itself doubled. And then what I can do is, for example, print that data just like I was before. Let me clear this, make sure that all worked okay. That looked like it did. I run the program. I get an error here. Access to memory that's already been freed. Where's this happening here? Print array. That should be okay. Size is 24. Let me just, is it happening here? So that's okay, yeah, so it's happening here. Excuse me. It should be 12. Oops. Did I not assign it? Oh yeah, you're right. Yeah, that's what it is. Thank you. I didn't reassign it back to array. So at this point it still had 12, and then when it was going to the 24, it was breaking. So yeah, thank you for that. Good catch. Who was that, Nathan? Recompile it. I'm still getting an error here. What's going on? Okay, this is fine, I think, because I never initialized the value, but I was hoping it would just reset it to, that's okay. So we can initialize this array again. Oops, array size, clear this. There we go. And now we've doubled the size of the array to have 24 elements. And that's the program I wanted to make. So, and actually, it doesn't really show it clearly here, but these first 12 elements still exist. You know, they get reallocated and copied over, and then, but although that's more than 24 values, isn't it? That should do 24 times. Or is it just that I didn't, oh, I know what it is. After I print, I should just printf a new line. To make that clear. Yeah, there we go. So that's the first time I printed, and this is the second time I printed with the 24 elements. And that's it. That's how we can use heap memory to make, for example, arrays. We can put other things in the heap. We can sort of put anything we want, really. And this is how we can use sort of dynamic memory. So we can put some data in an array. We need the array to get bigger, and we can put some more data in it, for example. Excuse me. Could I scroll up? Sure. And remember, this file is available on the course website. Okay, so I'm sure there's lots of questions and confusion about this stuff. What did we want to... That's the end of the lecture content, by the way, so if you need to head off, feel free. I understood everything except for the last 10 minutes. That's completely fine. I went through it a bit quickly. But all that matters is realloc takes some memory that you've already got and reallocates some more memory with the bigger size, and it copies the data that was in the original pointer. So if I reallocate this, it would copy that data into a new piece of memory and add more stuff to the end. And then it returns the new address, because if it's a reallocation, it's a new pointer on the heap. So realloc is like copy and paste. So fake olive, that's a great question. Realloc is change the size of the amount of memory I have and copy and paste. Nathan solved his eternal problem. That's really cool. Cyril says, is the original memory freed? Yes, that's correct. I believe. If not, you can free it. I'll have to double check that actually. So, yeah, I know the GIF you're talking about. I didn't know there was audio in it. Joshua, can we do stage 1 for assignment 1 with what we have learned so far? Absolutely. I think it's basically an arrays question. Okay, on this, we will schedule a assignment 1 live stream that's going to specifically focus on the content for assignment 1. This stuff is, I think, it's more assignment 2 stuff. When we get into linked lists and stuff like that for assignment 2. So we're going to have an assignment 1 live stream. I think we have to schedule it at some point this week. Or maybe we can even do it as part of the lecture tomorrow. That might be a good thing to do. Jacob says, and by the way, if you need to head off, that's the end of the lecture. Jacob says, what's line 20 to 26 doing? Great question. When we reallocate, we get a new pointer to a different spot of the heap with the new size of memory. So we're just making sure that that worked and that we actually did assign it. So make sure that it's not null. If it's not null, then we assign the original pointer to point to the new memory address with the new bigger or smaller data, and then we return that instead. Otherwise, we just return null because it didn't work. So this is just saying, did the reallocation work? If so, reassign that original pointer to store the new pointer, and then we return it. Okay, thank you all. Again, apologies that I'm not feeling well. Hopefully, I think I'm on the mend. I was much worse yesterday, so it should be better. And again, if you didn't understand all of this, that's completely okay. You can watch the lecture content again, and we'll have activities and things to get your hands dirty. So Ronald says, can you replace new p with my integer array on line 19? You could, but then if it didn't work, you would lose the pointer altogether and you wouldn't be able to free it, for example. So, yeah. Okay, thank you, Weena. Yeah, I hope I don't have COVID. Or if you're saying you have COVID, then that's not good either, Bondrick. Yeah, if you have lots of questions, that's fine. Thank you for the lecture. Get well soon. That's okay. Thank you. You're very sweet. Okay, thanks, everyone. Bye.